Okay, this is 13A, section 13A. I'm dividing into two separate sections. They're both related to maxima and minima, but I think they're different enough that they deserve sort of separate sections, keep them separate. So this one, I'll sort of give it its own title. This will be on relative maxima and minima. And so just to begin, let me do just a brief recall from Calc 1. So in Calc 1, we had the same deal. We had relative maxima min. So graphically, you might have something like this. You might have a function. This may be like that. I'll make this go forever, both ends. And then on this picture, you can find the relative minima. Those would be, for example, here, in blue. And the relative maximum, let's say purple. It's good. This will be relative max. So in this case, there are two of each. So we can have an official definition here, which can be sort of loosely interpreted or doesn't have to be exceptionally formal. We can say that a relative maximum is a point which is higher than nearby points, and a relative min is a point which is higher than nearby points, or which is lower than nearby points, right? So relative max, this is sort of formally, we could be, we have to be cautious. We could say not sort of higher than nearby points, but greater than or equal to. So here, f is greater than or equal to nearby points. And a relative min, this would be f is less than or equal to nearby points. So what we'd like to do is rephrase this in terms of functions of two variables, and then talk about how we're going to find such a thing, right? So just to stick with the recall, though, so in Calc 1, we had a couple different ways that we could find these things, these relative maxima and minima, but the standard way was through the derivative, right? So how did we do this back then? So I want to mention this. How do we find and categorize? Because it'll help us see why we do what we do in Calc 3. So the first thing we did was we found the critical points. So step 1 is find critical points. These are where either the derivative is 0 or undefined. Typically, we'll look at the case where it was 0, but formally speaking, it could be where the function is undefined, or where the derivative is undefined, rather. The function is defined, the derivative is undefined. So then, what we typically do for step 2 is we did the second derivative test. Right? So for each critical point, so we do a check. We look at f double prime. And if we get something less than 0, the way we think about it is less than 0 means concave down. And this tells it's a relative max. And if we did f second derivative greater than 0, this would tell us it was concave up. And this would tell us it's a relative min. And then if the second derivative was 0, then the test fails. We have to do something else, like the first derivative test. Right? Just there's no conclusion. So how does this work, like for functions of two variables? So let's formalize all these definitions a little bit, but we don't have to be too formal. We don't have to go crazy. So we'll say given a function f of xy, we say a relative maximum. So what this is, it's a point where the function is greater than or equal to all nearby points, right? So we'll say, we'll keep it a little more formal, like I said, is a point x0, y0, we're using that to refer to a specific point such that f of x0, y0 is greater or equal to f of xy for nearby xy. Now the word nearby is a little loose, right? Just like with a relative maximum is a function of one variable. As long as there's like a little region where it's the biggest or where nothing is bigger, then it's good enough. So this can be formalized using epsilons, but we're going to avoid that because it's sort of this good intuitive feeling. And I can draw a picture that'll help. This is a relative maximum. Let's bullet these, and a relative minimum. This is a point x0, y0 such that f of x0, y0 is less than or equal to f of xy for nearby xy. So a picture for something like this might be something like, so what I'm going to draw is I'm going to draw like a landscape. It's going to have, say, two hills and a valley. So the valley, well, the valley will be more like a hole. So imagine taking a plane and punching up through the bottom twice to make hills, and then punching down through the top. So you can think about this as the graph of a function. No idea what function would look like this, but it makes a good point. No pun intended. And then what we can see on here is we have two relative maxima. These are these points right here. I'll make the purple just so, because the other ones on the other picture were purple that way. It's a good way to see the correspondence. These are relative maxima. And down here at the bottom, blue, we've got relative minima, or a relative minimum. It's just one of them. So, same idea. We want to find what these are. Now, before I erase it, if you look back at the left-hand side of the page, right, just sort of embed this in your head. Step 1, find the critical points. So we're going to find the analogy for that. And then step 2 is do something with those critical points. Invoke some test. And that test will tell us something about the result. And so what we need to do is present the analogy for each of those. So that's what we'll do next. So this will be to find and categorize. So this is what we do. So in the one-dimensional case, we found the critical points. So same deal here. So find the critical points. I need to clarify what these are, but just get it into your head. The method is the same. So find the critical points. So these are points where either both of the partial derivatives are 0 or one of the partial derivatives is undefined. And again, like in the one-dimensional case, we're mostly going to focus on the 0 case because the undefined case is a little more quirky. So these are x0, y0, just to keep them specific, such that either first case, f sub x of x0, y0 is 0 and f sub y of x0, y0 is 0. Well, second case would be one of, well, let me say it this way, f sub x of x0, y0 is undefined, or f sub y of x0, y0 is undefined. We are almost always, in fact, always, not even almost, going to focus on this case right here. Right. So just a comment about that case. The reason that case makes sense is, for this one, think about if you have, say, a relative maximum, like this. If you go to the top of that and you draw tangent lines, in every direction they will be 0. So when we find f sub x, we're finding the derivative in the x direction, and the tangent line will be horizontal, slope is 0. F sub y is the derivative in the y direction, that would be 0. tangent line's horizontal. So in fact, every single directional derivative you could say would be 0. But for the sake of finding them, we find where those partials are 0. That second case that we won't do so much is not so relevant. It's a little more quirky. So we're going to find those critical points first. And then step 2 is like, great, what do we do with those? In the one-dimensional case, we found the second derivative, and that did it. In this case, it's not so obvious. So what we do is, first, we find this thing called the discriminant function. So the discriminant function is d of xy. So this is f sub xx times f sub yy minus f sub xy squared. So what this is, for those of you that have had linear algebra, this is essentially the determinant of a matrix. So this node, you don't need to know this node, but this is for some of you that might be interested. This is the determinant of the matrix like this, with the caveat that f sub xy and f sub yx will be the same in these cases, which we saw when we did partial derivatives, that f sub xy and f sub yx are pretty much always the same. And in these problems, they will be the same. So when you find this determinant, you get this discriminant. So that's where it comes from. And what this thing does is it sort of helps you figure out what's going on at that critical point. So then what you do is the following. You take each of your critical points. So for each critical point, x0, y0, you plug it in. Now, here's the deal. First case is if the discriminant is greater than 0. So this is not quite as nice. It's sort of like a very small multi-step process. If the discriminant is positive, this tells you it's either a relative max or a relative min, but it doesn't tell you which one it is. So then what you do is you then check either f sub xx at x0, y0, or f sub yy at x0, y0. If either is positive, then you have a relative minimum. Let me sort of sub-bullet this. And if either is negative, then you have a relative maximum. Now, this is all under the category. Let me sort of put some boxes here that help us sort of categorize all this and see what's going on. This is all under the case if the discriminant is positive. And then we'll separately look at if the discriminant is negative and if the discriminant is 0. But I want to make a comment here before we go further, because this might bother you. And you might look at this and you might say, well, what if one of them is positive and the other one is negative? Right? Like, could it be that f sub xx is positive and f sub yy is negative? And the answer is no. And the way to see this is as follows. Now, again, you don't need to necessarily know technically why it's the case, but for some of you that might be bothered by this, let me show you why. So this is just a little side note that you don't need to know. It might be interesting to you. So in this case, both, let me say it this way. Either both f sub xx and f sub yy are positive, or both f sub xx and f sub yy are negative. This is because, if you look at this case, this is the case where the discriminant is positive. So if you know that this is positive, then, and this is squared right here, then you know that f sub xx, f sub yy is greater than f sub xy squared. Now, the left side is positive, which means, the right side is positive, which means the left side is positive, which means these two have the same sign. So in this case, when the discriminant is positive, both f sub xx and f sub yy will have the same sign. They'll either both be positive or both be negative. So that's why you can check either, check whichever one you like, check whichever one is easiest. So we have the second bullet point. So if d of x0, y0, if the discriminant is negative, then this is what's called a saddle point. Now, if you've ever had a Pringle, which is delicious, you know what a saddle point looks like, because it looks like a Pringle, but it's called a saddle point. I don't know, maybe they didn't have Pringles when they came up with the name, or people. So I'll draw a picture so that you see. This would be a point that looks like, so imagine like the saddle of a horse is where the name comes from. So picture the point. Let's say we'll make this green, right on top. If you think about what happens at that point, in one direction it's a minimum, and in one direction it's a maximum. I mean, there are lots of things happening in different directions, but if you go sort of left to right on my picture, you'll be like a minimum. And if you go sort of in and out across the saddle where you put your legs, then it's a maximum. So that's what happens when the discriminant's 0. And then, last but not least, or when the discriminant is negative, rather. If the discriminant is 0, then the test fails. So in that case, it becomes much more complicated. We won't go there. Because there's no first derivative test. You need to do like more serious analysis. You need to dig around in the functions. So just to be clear, this thing won't happen for us. If it does happen, it's because you messed up in your derivatives and your discriminant somewhere. So this won't happen for us. Of course, it could happen in the real world, and you might have to find other approaches, but for us, nope, won't happen. So what I want to do is just work through a couple of examples. And this is pretty methodical. The one place that people generally make mistakes, let me sort of label some things on here before I erase it and do some examples, just to point out some of the tragic mistakes that people make. So tragic mistakes are finding the critical points. This will be a system of equations, and it's really easy to mess up the algebra in there, so be careful. The second thing is remembering the discriminant formula. It's not infrequent that people think it's a plus instead of a minus, or they forget the squared. So just be careful there. Once you get all that right, this is all pretty straightforward. So let's do a couple of examples. So the first one will be pretty straightforward. The second one will be a little trickier, but neither is particularly tricky. So we'll find and categorize all critical points for the function f of xy equals 3x squared y plus y cubed minus 3x squared minus 3y squared plus 2. So the process is find the critical points first. So first, find the partials. So I will say be careful when you do this, double check your work. It's really easy to make mistakes. And if you make mistakes in these partials or in solving, things can be a real mess. If you make a mistake in the partial derivatives, the result might be unsolvable, and then it's a mess, like a big, big mess. So f sub x will be 6xy plus 0 minus 6x. Clean that up a bit, because the derivative of the y cubed is 0. So minus 6x. That's that. That gets that equal to 0. We'll come back to that. f sub y. That's 3x squared plus 3y squared. This is a squared up there. Let me clean that up a bit. Minus 6y. That's equal to 0. So it's a system of equations. You can solve this in any reasonable way you can think of. Typically, you want to pick the one that's easiest. If you could pick one that's factorable, like in this one, in A, we can factor out a 6x. So I chose A because it's factorable. B is not factorable, right? There's nothing in there that you can pull out. It's not really obvious what you could do. But A, it's pretty clear. So this tells you either x is 0 or y is 1. Then we can follow both of those possibilities. Right? If x is 0, then I put it into B. So we get 3 times 0 squared plus 3y squared minus 6y is 0. So the first part vanishes, and then I can factor out a 3y. And then we get either y is 0 or y is 2. So what we get out of this possibility is we get two possible solutions, 0, 0, and 0, 2. And then we look at the possibility if y is 1. Put that into B. So we get 3x squared plus 3 times 1 squared minus 6 times 1 equals 0. So we get 3x squared. This is plus 3 minus 6 is minus 3. Add that to both sides is 3. So x is plus or minus 1. Divide by 3. Take the square root. Or rather solve it. So then we get two solutions out of this. We get 1, 1, and negative 1, 1. So let's just box these up. So we remember them. These are the 4 critical points of this particular function. So then what we do is we go down the line and we deal with each of them. We find the discriminant. So remember how this works. This is f sub x, x. Let me do this. Let me write it above it so we know what we're finding. We're finding this f sub x, x, f sub y, y minus f sub x, y squared. So f sub x, x. And we have the derivatives already, so I'm going to go back to f sub x and take its derivative. So f sub x is over on the left, right? We're focusing back on these two to do the next step of the work. So f sub x, x is 6y minus 6. F sub y, y is 6y minus 6. It's coincidence that they're both the same in this case. F sub xy is 6x, and that's squared. And then we just sort of run down the line, right? So we check all these critical points. So we check 0, 0. Now, you can, for what it's worth, you can take this discriminant, you can tidy it up and you can FOIL it, but it's not worth it. It's easier to just leave it and then plug the points in. So when I plug in 0, I get this. This is positive. So remember what happens if the discriminant is positive, then we check either f sub xx or f sub yy. They're the same here, but I'm just going to write f sub xx just to pick one. And I get negative 6, and that's less than 0. And so that tells it's a relative max. So just again, to remind us, the discriminant's positive, that says it's one of the two. It's a relative max or min. The second part of this tells us which of those it is. So we check 0, 2. So now when I plug 2 in for y, I get 6. 6 minus 0 squared. This is positive. Then I check f sub xx of 0, 2. Now for what it's worth, when I'm checking this, I wrote really more than I need to, because up in the previous one, this guy right here, this is this value right here. So I don't really necessarily need to rewrite it all. So like the one I'm about to check, f sub xx of 0, 2, is this one right here. So this one will be equal to positive 6. This is greater than 0, so it's a relative minimum. And we check 1, 1. So here we get 6 times 1 minus 6. 0, 0 minus 6x, which is 6 squared. This is less than 0. So it's a saddle point. Done. No additional steps. When we check d, negative 1, 1. So we plug in 1 for y, we get the same 0 and 0. Minus 6x, this is negative 6 squared. This is negative, this is also a saddle. It's not uncommon to have sort of a mixed bag of things like this. Relative max, relative min, some saddle points, things like this. So, pretty good example, not too many points, everything's pretty nice. The system that we solved in this one was really, really nice. So I want to do another one that takes just a little bit more work. So one thing to see is that the system in this one was really nice. And what I mean by that is when we look back here at A, this was immediate, gave us an extra y. Right? There was like nothing, there's no plugging of things like weird, like x equals 2y plus 1. Like it was very straightforward. It just started spitting the points out immediately. So I want to do at least one that doesn't. So let's say for this one we'll find and categorize all critical points for f of xy. So for this one we'll do 3x squared minus 6xy plus y cubed minus 9y. So process is the same. First, find the critical points. So we take f sub x, we get 6x minus 6y. That gets it equal to 0. We get f sub y, which is minus 6x plus 3y squared minus 9, and that gets it equal to 0. So in the first one, like the first one doesn't give us an x or a y like immediately. Right? However, the first one does tell us that x and y must be the same. Right? So from A. So and again, I'm picking A only because it's the easier one. In this case, it's got less stuff in it. It's easy to get something out of it. So you can move the 6y over and divide by 6. So now I don't have a specific x or y, but I have something I can then use in B. So I'm going to put this into B. So you can either put y in for x or x in for y, doesn't matter. I tend to like solving for x instead of solving for y, but so I'm going to put in x where there's a y. And now here I can divide by 3, and I can tidy it up a bit. So I'm going to get x squared minus 2x minus 3 is 0. There's factors. So we get x equals 3 or x equals 2. Now, to go with this, we know that x is equal to y from up here. So we get, if x equals 3, we get 3, 3. And if x equals 2, we get 2, 2. So easy 2 points. Then we do the discriminant. So we do f sub xx, which is 6. F sub yy, which is a little more confusing. This is 6. Well, not confusing, it's just a little bit more. Right? So here, we're not done yet, but just to make sure we're relabeling, this is f sub xx, f sub yy minus f sub xy squared. So f sub xy squared is negative 6. So f sub xy rather is negative 6, and then we squared. Then we check our 2 points. So we check, D, that should be of 3, 3. We get 6 times 18 minus 36. That's greater than 0. So then we check, again, doesn't matter if we check f sub xx or f sub yy. But here, again, we can just pick out this value, make this easy on us right here. This is f sub xx. So we'll say this is 6, which is positive. So it's a relative minimum. Then we check d of 2, 2. We get 6. 6 times 2 is 12, minus 36. That's less than 0, right? Because 6 times, well, actually, that's greater than 0, 2. Actually, now I get rid of this. I made a tragic mistake. Hopefully, you caught it a minute ago. I factored this wrong back here. I'm not going to re-record this, but hopefully, you caught it because back here over on the left, it's a very small change. This is my comment about making sure we solve things properly, and I need to follow my own advice. So this is x plus 1. So x is negative 1. So negative 1, negative 1. So then we check d of negative 1, negative 1. I'm going to double check that factoring, just in case, but I think we're good. So now we have 6 times negative 6. 6y is negative 6 minus 36 again. And this is less than 0. So it's a saddle. And that's it, done. So yeah, apologies for that little screw up over there, but maybe you caught it. Maybe you were a little worried until I called that mistake. But in this case, just one relative max, just one saddle point. So let me just do one more. I'll do one more. I want to do this one. This one's actually a really fast problem, but I want to do it because I want to point out the problems that look icky can turn out to be okay. So we'll find and categorize all critical points for f of xy equals y e to the x minus 3x minus y plus 2. So it looks icky because of the e that's in there. So you might sort of be concerned about how that comes out. But really works out okay. So first, find the critical points. So f sub x is y e to the x minus 3. That gets set equal to 0. F sub y is e to the x minus 1. That's equal to 0. So we see that it's actually pretty nice because b gives us something immediately. So b is certainly easier in this case. We get e to the x equals 1. So x is 0. If we put that into a, we get y e to the 0 minus 3 is 0. So y is 3. So we get a single point. 0, 3. Find the discriminant. So we do f sub x, which is y e to the x. F sub y, which is 0. Minus f sub xy, which is e to the x squared. So you'll notice that the first term is 0. And the second term is positive. It doesn't matter what you plug into it. But just to be extra sure, when we plug this in, we get 0 minus e to the 0 squared, which is negative 1, which is less than 0, so it's a saddle. And that's it, right? So really quick problem that sort of maybe looks a little harder at the beginning because of the e in there. So that is the end of that section.